Oh, hello. This is Andreas Lange, Teledyne DALSA, European office here in Munich. And instead of talking to you at UKIVA in Milton Keynes, I'm trying to do this in an online version. So, welcome to this presentation. I'll talk about next generation line scan technology, things that we have ideas of in the pipeline or perhaps already in a product. This is the overview, what I'm talking about, the agenda. Talk about latest CMOS TDI technology, high-speed imaging, all combined with the above. We talk about multi-field, multispectral imaging, have a word about super resolution, talk about camera interfaces, and shortwave, infrared line scan imaging, and we also look about low to mid-range applications because this is still an interesting market. Quick recap of what line scan imaging is. The easiest thing, be it CCD or CMOS based, is one single line of a sensor. Next step was dual line, very easy to manufacture and to align. Exists also for CCD and CMOS, gives better responsivity and signal to noise ratio. And then what we are quite good at Teledyne DALSA is TDI sensors and cameras. Time, delay, and integration, multi-lines in the sensors up to 256 lines in CCD. An object point is imagined on the same pixel of each line. The charge, the responsivity is added up and gives, at a high line rate, very high sensitivity. And if you tell your engineers, hey guys, what would you like to do if you come up with something fancy? And they show you something like this. Why not do a combined TDI array of one sensor block, which we call here the main array, with 128 lines, or rows as they say, or 64 lines, pixel size 5 by 5 microns, a little bit of electronics on each side of these blocks. And well, we could do this in a mono version, and when we output one image from this array and one image from this array, we could do HDR imaging, for instance. Sounds quite neat. And just to give you a little bit overview about what this brings, what the big advantage of this is, here we've put together a comparison of the obsoleted high-resolution CCDs that we did, comparing to the TDI CMOS. So slightly higher resolution, but pretty much the same pixel size, 5 microns. But the biggest advantage, of course, is with CMOS, you can run at the same or slightly higher resolution much faster. We have fewer number of stages. It's marked green here, so it should obviously be an advantage. And in the first slide, I said, well, the more stages, the better. But the more stages, the more challenging it is to have your system geometrically well aligned and the object transport highly precise in a linear fashion. So 128 is really better for the setup and alignment. And you see, we still, with modern CMOS technology, get a much better responsivity. We have a lower read noise and also reduced NEE, noise equivalent exposure, as we call it here. So how much light do we need to discriminate just from noise or see, oh, there is really something going on in the object and the pixel reacts to that. Dynamic range is better than that, better than in CCD. In different operation modes, yeah, the signal noise ratio is pretty much the same, slightly the better, so comparable to CCD. And the MTF spatial resolution is also increased. Now back to this fancy dual array, which by the way can be done also in 3 arrays. We could do RGB, 128, 64, 64. Well, the idea is that we could even do a quad array thing, RGB combined with 1 mono, 4th mono array, or RGB NIR array. Something that was not clear from the first slide here is that we have a little gap. We need space. We actually need 35 lines, each of 5 micron height here, because we need readout electronics on top and bottom of each of those arrays. And this has a slight drawback concerning geometry here, because you can imagine if we introduce here another 175 microns, the sensor gets longer from the very first to the very last pixel. So the alignment is a little bit more critical, and spatial correction, geometrical correction can occur, especially if you use wide-angle lenses. And this has to be compensated for, and we're not doing it in future cameras, but our frame grabbers are ready to compensate for that, especially in the RGB version, if we ever do that one. The diagram I've used so far always was with a mono main array, 128 lines, second array, 64 lines. But that's not fixed. You can actually select the number of lines used in each array. Standard in the HDR mode is a ratio 2:1. You could use 4:1 if you have to well, even higher contrast and more bright and dark objects that you need to discriminate, and you can even go to a ratio of 8:1 here. And by this switching of stages in each array, you can control the slope of this response ratio curve, as we call it. Currently, oh, by the way, I didn't mention that for the image is fused in a frame grabber, not in the camera. Camera operation modes, yeah, as we said, well, actually I did not say that yet. The main array can run low, 16K wide, 128 stages, and standard TDI operation for general imaging. Line scan is line speed is up to 300 kilohertz. Yeah. HDR mode, what we already spoke about. Main and second array each runs at 150 kilohertz, gives 300 kilohertz combined. A little bit confusing because we mentioned that combined in our data sheets. HDR for images where you need to discriminate bright and dark objects. You can also use both arrays with the 64 lines. You get a combined line rate of 150 kilohertz. High full well mode is, as we call that here, for very bright scenes with a very, very high range from the lowest, from the darkest to the brightest, where you just need to fit high dynamic range into that one. And we have an area mode, which cannot be used for imaging because the charge from each line is not summoned up, it's just giving each array its own, so the image looks very bad. It's very fast, and it can only be, due to the bad image quality, it can only be used for mechanical alignment, but it's very useful for that operation. Okay, next topic here, multispectral versus multi-field. Multispectral, quite easy, capture the same object but with different illuminations, wavelengths, either simple RGB or maybe UV or throw in infrared. As said, we can combine mono sensors, we can have RGB, infrared, or what have you. Multi-field is usually just one type of illumination, sometimes only standard white LEDs, but it illuminates the object from different angles, bright field, dark field, backlight. But why not combine both? So we have multi-field combined here with multispectral, with RGB lights, continuous with LEDs. That's represented by those curves here. Here we have the multi-field with a multicolor, just multispectral, multi-field and multispectral. This one, again, these are the curves, the illumination curves of the continuous with LED. And these filters, dichroic filters, is what we have on the sensor. Dichroic is some kind of interference filter compared to standard pigment-based filters, and they give a very steep separation of one color against the next one. It's the big advantage of dichroic filters. Little more expensive, actually quite expensive in the manufacturing, but yes, for critical color discrimination, you just have to use dichroic. It's one of the many options you have in multispectral or multi-field imaging. What else? Yeah, 16K resolution was what we spoke about so far, 8K or 4K. But yeah, sometimes it's not enough. Flat panel display inspection, you need to find even smaller defects in the next generation. Find a defect of 1.5 or 2 micron reliability would either require very big sensors, 32K would be fine, or very small pixels itself. With very small pixels, like in area sensors or what you have in your cell phone, pixel size below 1 micron, they are very unsensitive and you just cannot get enough light on the scene. And the lenses for a big sensor, 16 or more K at 3.5 micron, even smaller lenses would get big and very, very expensive. So we came up with the idea, which is not really new, it has existed in area scan for quite a while, where a sensor was by piezo motors, pixels were shifted. Here we have the array that we mentioned before, many lines here, many lines in the second array. Just the drawing just has 2 lines here, but actually it could be the big arrays we've seen before, with a slight offset of half a pixel, and combining this in the camera would enable you to use a 16K standard lens, 5 micron, and detect very small pixels at a much higher signal noise ratio compared to the single 16K sensor. It's quite some fancy things. We'll probably put that in a camera very soon and we'll see if it's as useful as we thought. Lots of data coming out of the cameras. High resolution, 300 kilohertz, 400 kilohertz, or even more. That's way beyond what Camera Link or other standard USB, what have you, interfaces can do. Many of you may know that DALSA was the inventor and propagator of the Camera Link HS standard based on InfiniBand technology, GIGI server technology. Actually, it's not that much different from 10 GeE. The physical core is pretty much the same as we have 10 GeE, packet-based interface over copper. First, there was the so-called M protocol for bandwidth up to 3 gigabit per second. Now the X protocol supports higher bandwidth. Problem with X protocol is that you cannot use copper cables anymore. You need active optical cables. So there's a small converter here, actually an optical fiber cable, directly in the connector here. Goes up to 30 meters or even more. Quite flexible and an interesting resolution. Solution. What we also had, which is surprisingly successful, is just put directly an optical converter SFP plus in camera and transceivers and receivers into the frame grabber, and then you can use just standard telecom fiber optical cables. Price has gone down with increased usage of this in telecom or internet providers with fiber optic use, patch cables. So the price is below £1, euro, dollar per meter. They are very, very robust meanwhile, and big advantage for industries where you have motors, electric fields, electromagnetic fields. They're immune to anything of that. So they're very popular, let's say, in the printing industry. We have big motors running and very cheap and easy to install and maintain. Transceivers, standard transceivers, which are cheap, can easily support up to 300 meters or more, but you can actually go to 1 kilometer or even longer. So that's surprisingly popular. We've just had this as an idea, but seems to be accepted very well by customers. But there are also frame grabberless interfaces. For example, N-base-T, that's cameras here from our sister company, Teledyne DALSA. They have very nice slide scan cameras based on N-base-T. It's just the trademark for 5 GeE. Teledyne DALSA also does coax express. We need frame grabber, just want to mention it. We at DALSA don't have it in line scan cameras yet. We have it in area scan cameras. But so coax express should also be mentioned. N-base-T likely to replace camera link in the long run. Well, not so convinced about that yet, but we may see. What else is in the future? Oh, why not shortwave infrared, SWIR imaging, depending on the definition that you use, 900 to 1700 or 700 to 2500 nanometers range, cannot be done on standard silicon-based CCD or CMOS sensors. It requires N-gas detectors, indium gallium arsenide. What can you do here? Well, in science, you can see geological information, mineral content, vegetation, water, special patterns that you cannot use here. Well, that's the coastline. You can actually see under the coastline through the water. Very nice. What can a SWIR do? As said here, see through water, image through glass, differentiate colors, sort of thermal imaging, moisture detection, night vision. Some applications here, science, security, military. Well, we are at the machine vision conference, so we talk about sorting, crack detection in glass, fill level. But what we see so far, the main interest is food sorting, recycling industry, plastics, well, obviously the same, but well, in standard visible, looking the same, but very easy to discriminate. And also some very interesting in the solar industry. That's about SWIR imaging. So that would be the responsivity curve of a standard CCD array. That's the responsivity of an InGaAs detector. Actually, on the sensor itself, you have the standard silicon readout IC ROIC, which defines the quantum saturation noise linearity to control that, and the InGaAs detectors on top of that one with some very fancy interconnects. And this curve brings me to a point that's very important, which not everybody keeps in mind when trying SWIR cameras. This would also be the sensitivity curve, responsivity, bandwidth of standard machine vision. It's because the anti-reflection multi-coating on standard lenses cuts off here where InGaAs really starts. So if you want to check that out, keep in mind that you get a SWIR lens. Well, pretty much all of the big lens manufacturers have them, but make sure you have one when you try a SWIR camera. Yes, so far there was very high-end, high resolution, top of the line, very high line rate. But that's mainly in markets in Asia, flat panel inspection, electronics inspection, but not every customer needs that. I mentioned recycling food sorting, and this is standard to low resolution sensors and quite moderate line range, which could easily be going through base, camera link, or even gigabit Ethernet, standard GigE cameras. And these customers have used CCD sensors in 1-2K resolutions and up to 5 or 10 kilohertz since 10 years or longer. And they hear CCD will be obsoleted and say, well, will you let us down, DALSA? You're stopping CCD. Well, not for this year or next year, but then at one point CCD line scan will go the same way as CCD area scan has for the big manufacturers that stop just doing the CCD area scan. And so, no, we won't let those customers down. We have the idea, quite progressed idea, to do CMOS sensors, most likely in multi-line configuration with very nice, good old pixel sizes that standard lenses can do, high sensitivity, not so expensive illumination required. So CCD will be mocked, as we hope, by CMOS sensors to keep the customers happy who don't need the most expensive and the fastest and the latest and the greatest stuff, but are quite content with what had existed in the last 10 years. Okay, thank you. Hope it was interesting. If you have any questions, contact us through the Teledyne DALSA website or the UKIVA website. And I hope we'll see each other next year at UKIVA in Milton Keynes 2021. Thank you.